Hello everybody, I'm Andy. I'm talking about the approximate dynamic programming for my research. As we have learned in class, the dynamic program uses the ability to solve optimal decision problems, but it also has the limits to use for the small or simplified real problems. So we introduce approximate dynamic programming. We also say as ADP. It does not need to calculate every possible state for the problem. It just do performance of the approximations for the states and do iteratively improve by means of simulations. Compared with dynamic programming, it through the dimensionally limitations of DP algorithms while it still have DP's advantage. Approximate dynamic program can divide into 4 groups. The first one is simplified as HDP. Second one is DHP. Third one is ADHDP. We also call it Q-learnings. The fourth one is ADDHP. Okay, in these presentations, I will show how to use in 3 cases. The first one will be like discrete time nonlinear XJB system. The second one is optimal trading in the electricity futures markets. The third one is control of an autonomous vehicle. For discrete time Hamilton-Jacobi-Bellman equations, we use HDP iterations, which does not require initial stable policy. It derives the values of the value functions of the problem with continuous state and actions. It provides a learning method based on the learning method based on the continuous state and actions. It also uses the neural network structures to approximate the optimal policy and value functions. Okay, the algorithms of the HDP is like, if there is an input nonlinear dynamic system as x is equal to f plus g times u, and then we need to minimize the cost function of vk to find the control policy of uk. As we know, the cost function can be rewritten as this formula of v of xk is equal to this one. It's like for the HJBC, it comes with the v star it comes with the the same functions just instead of we stop, and then take the derivative respect to u of k, and of this formula we say equal to 0, and then we get the optimal controls u star. Then get back to the HJB equation. So we have the values functions of v star to be fine. So as the control of u of norm is equal to the mean of the quadratic functions, then the cos v1 will be fine. And we have the use the HDPs to get the iterate as state of the cos value functions. So the flow diagram is like this. When we started with the v0 is 0, and then find the minimize problems as dealing with the value function, and then we make a decisions yes or not, and then make a update and go back to the minimum problem again, updating, make the decision, and then do it the closed loop until it go to finish. For example, if we have the nonlinear system like this one, with the values functions and the control inputs, then the phi of x will be like the vectors of the network approximates to the value function. Wv is the weight of the functions. And this one will be the vectors for the network approximate of the control. With the MATLAB calculations, we will get the results for the value functions weight is converged to Wv of t, and the control weight is converged to these numbers, these vectors. Okay. So now I will show you the results of the state trajectory for the difference between the state dependent negative equation and the HDP algorithms. From the graph of left, you will see the trajectory is mostly match of each, and from the graph on the right, the trajectory will match after a time step of 3. And then the graph on the left will show you the cost for the two methods. As we can see that the cost we found using the HTTP will be like much lower than the other one. So for the graph on the right is to find the controls inputs between two methods, and it will show us that the controls for the control input for the HTTP the approximate dynamic programming is most likely constants. So the HTTP is like a good way to find the feedback controls for the corresponding discrete time HTTP equations. Now we go to second case. This one is called optimal trading in electricity future markets. The problem is like we have generators. We decide to sell the future energy productions in advance, and find the markets with minimum in a variance of benefits. During the training, we have some risks like the transmission links and the shortage of the supplies. So our goal is to maximize the profits for the training and also limit the risk. Okay, the first one is the profit equations, where W is the numbers of realizations. This one is called the income we sell for the of the energies, and this one is the cost of the energies we need to spend. And the last one is the market transaction cost for all the energy we sell. The second equation is Rx with the risk functions. To find the values and the risk of these total functions. As so before, this one is the income, this one is the cost of the energy, and this one is the market transaction cost. Okay, the flow diagram for this case is like we have initials, we have to make the approximations and come to the decisions. If it's not, we have to update the states and make the decision of the maximize the value functions and do the simulations and find the profits for this period, update, and go to the loop again until we get the convergences of the value functions. So the algorithm is like for the under the iterations, the first step we have to make the decision of xk is the energy sale during the hour t under iterations of k. So like this x will be 3 properties. The first one is like 85% will be like the values of the last one, or will be the value functions of last iterations. The second way is 10% for the any numbers. The third one is like 5% will be like stay the same with like stay the same with the last one. And then second step is find simulations of profits at time period of t. Okay. Then we find the various functions. Find the various function of and the time period t with the iteration k, where theta is the parameter vectors for the approximations, and phi is the nonlinear basic function for the expect profits. And then go to update iterations until we go to the converge, where the value functions v of t is still staying the same for the iterations of k. So okay, with the help of MATLAB functions, we have the resource like this one, where the blue line is the expect benefits of by DP programming or dynamic programming, and this line, the top line, is the benefit for the approximations dynamic programming. As we can see from this graph, the benefits for ADP is always greater than DP, and the risk for ADP, which is here, is smaller than the risk of DP dynamic programming, which one is here. And from this graph, we can also see that when the initial percentage of energy flow is about like 25 or 30, all of the benefits will like stay constant or stay relatively constant. Also, from this graph, we can see that this one is for the energy cells in by ADP programming. It's like for the current price, about like 50 to 70% of it's like the mostly balanced to make the expect benefits. Okay, and then we come to the third case of use. It's like the pace flowing control. With it's usually with the developments of the intelligent transportation systems, the applications is increased with the military and aerospace. They need to find some intelligent control methods for the autonomous vehicles. But the difficulty is they have to face the complex environments with a lot of uncertain parameters and nonlinear characters of the vehicles. Okay, so for the autonomous vehicles, the dual heuristic dynamic programming is used to control the steer angles of the wheels. They have to calculate the near optimal solutions with large states and action space. It's not exactly the optimal solutions for all of the states. Compared with the other methods, during the interactions with the environments, the DHP algorithm does not require the needs of the teacher's signals. It will learn the optimal control policies by itself. Okay. For the kinematics modes of the vehicles, suppose the vehicles is initial with starting like this, and at time of t. So when the moment of t plus 1, it go from here, this one, back to here, and then the coordinates of the new place, it will show like this. X of t plus 1 is equal to x of t plus L, which is this one, times the sine beta of t, this one. And the y coordinates at moment t plus 1 is equal to y of t plus L times cosine beta. And heading angle is phi of t plus 1 is equal to 90 degrees minus beta and minus alpha, where alpha is equal to v times tau times t times g and times theta divided by 2L, and this L is equal to 2R times sine theta, where R is the radius of the wheels. For the easy calculations, when tau is small, it's like when tau is like equal to 0.05 seconds or 0.01 seconds, then the radian values of the angle were like really close to the sine values of the angle. It'll be like the have the L is equal to 2R sine theta. We're close to V times tau. And then the the coordinates of the vehicles will be x of t plus 1 is equal to xt times L times cosine lambda of t, and y is equal y of t plus 1 is equal to y of t plus L times sine lambda t, and the new heading angles phi of t plus 1 is equal to phi of t plus v times tau times t times g times theta divided by L. Where the lambda of t is equal to phi plus v times tau times t times g times theta divided by 2L. Therefore, we go to find the states of the vehicles when they during the interactions. The state will have the functions s of t is get involved with d theta lambda phi and the speed v of c, where d is the errors of its like relationship between the position and the load. Delta phi is the relationship between the vehicles and the directions of the load. Dt dot is the change of the error, and delta phi dot is the change of the error between vehicles with the directions. So to find the state S, we also have the state vectors. It's like it's calculated with the vehicles go to point of P. If I have dt d dot of t delta phi dot. Okay, then we can we have this formulas for the state vectors at moment t plus 1, but I don't go through all of this. The DHP uses the autocratic structures, which has 3 backpropagations neural networks to realize like this flows. You also need to calculate the weight values W for the created networks and the alter networks. Because of time problem, I don't go through all of this. This one is the frameworks of the learning control. As this one is we have to make the decision to sure it's the end of the studies to make the actions. This one is at networks to go through the cars or models, and then go back to critics networks 1 and critics 2 with the reward functions of respect to the partial derivative of the actions and the states to go to the end of the studies. Okay. Now we make simulations with the MATLAB programming. This one is the suppose we have the load include two tangents, and the tangency point is P. The radius of the load is the radius of the tangent is 20 meters, and the speed is 10 kilometers per hour. These simulations will test the performance for the fixed load and the performance when the vehicles pass through the point of P. Okay, so these two graphs will show the curves of the moving stations for the between two different methods. The first one is the under DHP. The green line is the path, and the red line is the actual path of the vehicles. As we can see under the kinematic models, the red line is not or go along with the green lines. That means it's under the kinematic models. Under the kinematic model, the actions is hard to flow what we expected. Okay, this one is showing the heading angles of the vehicles under DHP and then the kinematic model. As we can see, under DHP algorithm, this graph will be looks much less than the other one. So the conclusion is like, even though use the DHP, but when the vehicles are moving interactions with the environments, the realization is more complex than we have expected in the lab. Okay, yeah, that's my reference of the research. Okay, thank you all.